So now we've basically finished these generic understanding of reactions. We've seen a lot of specific cases where these generic reactions can occur. And now I want to transition into understanding the physical properties of molecules, or that is organic molecules, right now specifically around pH and solubility. So how does pH affect solubility? Well, in Chemistry 5, we talked about acids and bases. So in the 5th chemistry lecture, we talked about Ka, pKa, etc. And we've been talking about it in this session and in the first organic chemistry lecture. So those are really important concepts in this transition to organic chemistry. And we talked about the half equivalence point, pH equals pKa, right? The transition between when most of the acid is protonated or most of the acid is deprotonated. Or for that matter, a base, when most of the base is protonated or when most of the base is deprotonated. When the pH is below the pKa, most of the acid and the base are protonated. The way I like to think about that is a low pH indicates a very high concentration of protons. Right? So I have a lot of these protons floating around. That's in a low pH. So if you've ever gone biking in the spring around usually some wet areas, whether it's grass, with a ditch or a river, even if you haven't, I know that's a relatively specific scenario. Imagine yourself sort of biking along this river, and earlier in the spring and sometimes later in the fall, these gnats like to fly around. Okay, and the gnats fly in almost like these congregations, these blooms. Like they'll take up this almost spherical-ish space. It looks like a school of fish, but it's gnats flying around in the air. And when there's a very high concentration of those gnats, and you ride your bike through them, right, you can avoid them really, really easily when you're walking because you sort of duck your head, but it's kind of hard when you're moving 20 miles an hour. When you fly through these practically, if there's a high concentration of those gnats, you're going to get some getting into your face, like go in your mouth or sometimes into your eye, which is incredibly unpleasant. And so the more gnats there are, the more likely it is that you will have some attached onto you, that you'll get some on your face. So you can think of the protons like that. When you have a very high proton concentration, it's much more likely that your compound will be protonated, whether it's an acid or a base, because you have lots of protons available. But as those gnats start to die off, there's fewer of them in the air, and so you might even pass through some of those schools, some of those clouds of gnats, and not get any collisions with your face. Again, because the abundance is very low. So when the pH is much higher, when there's a very low concentration of these gnats, it's much less likely to find one attached onto, much less likely to find a proton attached onto your molecule. So when pH is below the pKa, most of your compound is protonated. And when the pH is above the pKa, you have a lower proton concentration, most of your compound is deprotonated. That is true for both acids and bases. The consequence is just not the same for the two molecules. If I have an acid, the consequence of protonation is that it's uncharged. There's a protonated benzoic acid. The consequence of deprotonation is that it is charged, so it's going to be highly soluble. Charged, so pH below the pK, is going to be mostly insoluble. So pH below the pK, protonated, uncharged, is low solubility here. High solubility is when it is deprotonated, when it is charged. Okay? So that's for acids. For bases, it is the opposite. For bases, if it's protonated, so that is pH below the pKa, the compound will be charged. if it's protonated. If it is deprotonated, it's going to be uncharged. And the rule is when a compound is charged, it becomes very highly soluble in water. When a compound is uncharged, it's less soluble in water. Don't think of this as like dissolves like. So if I treat an acid with an acid, it'll dissolve. No. This is not a physical sort of intermolecular property deal, which is where like dissolves like applies. This is a chemical reaction. You want a deprotonation or a protonation event to make it soluble or insoluble, depending on whether it's an acid or a base. You must understand this concept fluently. Okay? And so let's try out this problem. Okay, so at a pK of 4 or the molecule has a pK of 4.1 at a pH of 3.9, is the conjugate base present in solution? Remember the titration curves. So my titration curve will look something, that's a little bit too big. Titration curve will look a little bit something like this. So this is the pH, and this is the volume of base added. So if my pK is somewhere around here, that's roughly my half equivalence point. And I'm right here. Is the conjugate base present? Yeah, absolutely. It operates on this gradient, right? There's this spectrum. Very little is present here. A lot is present here in terms of the conjugate base. And I still have very little bit more. And you can see that it is sort of this gradient in terms of how the quantities increase as you add more base. So don't think of pKa as sort of this switch. It is either protonated or deprotonated. It's a gradient. pKa is just the threshold where most of it is protonated, more than 50%, or not most of it is protonated, less than 50%. Okay, so will conjugate base be present in solution? Yeah, absolutely, because you're really close to the half equivalence point. Okay, so my answer here then is B. So let's try this practice problem. Okay, so this is a generally more complex question than what you would see for something comparable on the exam. They'll usually ask you more straightforward solubility type questions in terms of basic intermolecular properties. What I want you to recognize about a lot of these molecules is that, again, like dissolves like, when we're talking about intermolecular properties, and molecules, and this is the part that's important, molecules that are not too much larger than things like ethanol and propanol start to very quickly become insoluble in water. Okay, so they can very rapidly become insoluble in water. And just to sort of illustrate that, if we look at something like methanol, it's very soluble in water, right? Ethanol, also quite soluble in water. When the water gets very cold and the ethanol is very cold, you can actually get them to separate. So they're not highly miscible under all temperature, at all temperature ranges. You have to be very careful not to mix them, but they can be separated. Propanol and water can mix relatively well. Not super well, especially if they're very cold, but they can mix. Now, by the time you get to butanol, it's already almost completely insoluble in water. The solubility of butanol in water is something like 2%. It's tiny. And butanol is not very big, right? This is butanol. It's got a pretty low molecular weight, not that many carbon atoms. It's not, it's mostly nonpolar, but it's not that nonpolar. It has a hydroxyl group there. So very quickly, organic molecules become insoluble in water. Because water is quite polar, the protic solvent. For frame of reference, I've drawn a molecule here that has this molecular weight of 259 grams per mole. You don't have to be able to reproduce this on the exam. I just want you to have an appreciation for what this size means about a molecule. And this molecule is not going to be soluble in water. It's quite large, much larger than butanol. It doesn't really have any charged groups on it. Amides, ketones, and alcohols are, yeah, they're polar, but they're not that polar. The only one that's probably the most polar is the hydroxyl group, and it's just one out of a pretty large compound. So it's not going to be very soluble in water. Now, it's not totally nonpolar either. And hexane and dipropyl ether are very nonpolar solvents. They'll probably dissolve into them, but acetone is going to be our best bet. Acetone's a nice intermediate solubility. Again, there's a little bit beyond the scope of the exam in terms of the difficulty here in sort of separating these on this gradient of potential solubility. So you'll see these questions come in a more straightforward form, but it's still a very interesting inquiry into, what does it mean to have a molecule about this size? What can we extrapolate about some of these different functional groups and their corresponding solubility in different solvents?
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.